Hey guys, welcome to day 10. This is kind of carryover from yesterday. We kind of focused on the amount of energy that it takes to break individual bonds. We kind of focused on how much energy is released when new bonds are formed. Today we're going to do some kind of full-fledged problems. I've provided you with the bond energies in the assignment. They're also in the copy of the notes, so if you guys need those, you can look in the textbook or you can just look on the page here. We know that it takes energy to break a bond, so that's going to be positive energy, that's going to be endothermic. And when new bonds are formed, energy is released, that's going to be exothermic. But when we actually start to use the equation, we don't actually use positive and negative values. And the reason being is that we start with the energy spent to break those bonds, but then we subtract out the energy that's released. So in the end, we kind of we realize this is represented, since we're finding the difference, it does represent a negative value. What I've done today is I've kind of just given you some problems, and I put copies of them in the lecture so you guys can see what you're doing as you're kind of going over your homework. Now, the name of the molecule is a little bit different in the diagram than in the textbook. That's okay. But we're looking at how much energy it takes to, and I'm going to color code these. We want to break the bonds over here, and I think we've done those in blue. So that's going to take some energy to do that. But then on the right side, we are going to make some new bonds. Now, if we look at these two structures side by side, none of these bonds are broken. We're not breaking any of the carbon-hydrogen bonds. So those are identical. We are not breaking this nitrogen-carbon triple bond. It's present on both sides of the equation. So really, the only difference between the left side and the right side of the equation is this bond and this bond. So keep it simple. We're going to say 1 mole, and I'm going to change my color so it kind of follows suit. 1 mole of methyl isocyanide is taken apart, but really, to keep things simple, we're just going to look at 1 mole of these carbon-nitrogen single bonds. And if you come over here and you look, it's going to take about 305 kilojoules per mole. So 1 times the 305, and the 1 stands for mole. So this is how much energy we have to spend to break the bonds on the right, and I'm going to go ahead and put this in a bracket because that's all the bonds that are broken. And then what we're going to do is we're going to subtract out the amount of energy that's released when new bonds are made. So if you look at the right side, we are going to make 1 mole of carbon-carbon single bonds right there. So I'll put it in brackets again since we only have 1 bond that's being made. We're going to say 1 mole of carbon-carbon single bonds, and we look over here, and the bond energy is 347. Guys, I just want you to realize something, that this number 1 represent moles, so we're actually kind of canceling out kilojoules per mole. And same deal here. We have 1 mole, and it's basically kind of canceling out part of the kilojoule per mole. Just part of the bottom of the part of that equation. So running out of space over here, but you get the idea. So basically, you're doing 305. That's how much energy you have to spend in order to break the carbon-nitrogen bond on the left, and you're going to subtract out the 347 kilojoules, which is the amount of energy that you get back. So all in all, this will be a negative answer. And a negative answer indicates that it is going to be exothermic and likely to be spontaneous. So I'm going to let you guys do the math on that one. All right, let's look at another example. Okay, acetic acid is responsible for the sour taste in vinegar. It can be manufactured using the following reaction. Okay, let's look at this a little bit closer. We have, let's go ahead and draw these structures out. So this is your methanol, and we have an OH with a single bond. I'm not going to draw out the carbon monoxide, but I am going to go ahead and I'm going to draw out the acetic acid. So you have this meth group, the CH3 group over here, connected to another carbon with a double bond to an O to an H. Now if you look at the left side and the right side, I'm going to try to color code things for you. This bond, and this bond are really identical to this bond, and this bond. So you could do the math to break those 3 bonds, but then it would kind of wash out in the end because you're going to make those 3 bonds again. All right, let's look at some other things that are the same. This OH bond is identical this OH bond. So you could calculate the amount of energy needed to break that bond and make that bond, but in the end, it's all going to kind of cancel out. So let's do things that are blue on the left. So now we have, I'll call this bond number 1. We have 1 mole of carbon, oxygen, single bonds. And that's really going to be the only bond that needs to be broken on the left. So we can say that 1 mole, and we've come up here and we look at the number, it's 358 kilojoules per mole. And that's going to be the total amount of energy that is spent on the left side to, well, actually, I need to take one more thing into consideration. I forgot about this CO right here. So we're going to call this bond number 2. So then we're going to come over here and we're going to say plus 1 mole of carbon monoxide. So that's going to be a triple covalent bond. So we come up here and we say, okay, here's our triple covalent bond for carbon and oxygen. So 1 mole of carbon monoxide. It's going to take about 1,072 kilojoules to break all of those bonds. So now we have everything on the left side. So we broke this bond number 1, this carbon-oxygen single bond. We broke this bond number 2, this carbon-oxygen triple bond, and the sum of those two values should be in the 1,400 range. Now, let's look at how much energy we get back on the right. Okay, I'm going to change to red. So now we're going to subtract out the new bonds that are being formed. So I'm going to call this bond number 1, that carbon-carbon single bond. So 1 mole of carbon-carbon single bonds. Come up here and look at the chart. And where is it? There it is, 347. So 1 mole of carbon-carbon single bonds would be 347 kilojoules per mole. And then we're going to look at, hey, here's this bond number 2, this carbon-oxygen double bond. So we're going to add 1 mole of carbon-oxygen double bonds, and if I look up here, it's 745. And we also are going to, we're going to call this bond number 3, this carbon-oxygen single bond. So 1 mole of carbon-oxygen single bonds is going to be this 358. So 358, I'm running out of space, that would be kilojoules per mole. And when you realize, actually this carbon-oxygen single bond right there is really kind of identical to this carbon-oxygen bond over there, but just realize we had to break it and then we had to make it, so it is going to kind of cancel it out in the end. So if you guys wanted to go ahead and do the math, you can do that. So all the numbers in blue represent the bonds that are broken. We broke the carbon-oxygen single bond in methanol, and we broke the carbon-oxygen triple bond in CO. And then we made a couple of bonds. We made 1 mole of carbon-carbon single bonds. We made 1 mole of carbon-oxygen double bonds, and we made 1 mole of carbon-oxygen single bonds. So if you guys want to go ahead and do the math, should lead you to the right answer. Just realize, guys, moles and moles and moles and moles, they're all kind of canceling out in the end. I know I kind of didn't show all my units in the end there, but just realize the kilojoules are going to remain and the moles are going to cancel out. All right, a couple more examples. For this one, I've given you some pretty big hints. You're going to get 2 moles of SH bonds, because if you count them, there's 1, 2 moles. And you're going to get 3 moles of fluorine, fluorine single bonds. So these are the bonds that need to be broken. Okay, and then on the flip side, we're going to subtract out. Look at this. We're going to make 4 moles of sulfur fluorine single bonds, plus we're going to make 2 moles of hydrogen fluorine single bonds. So I've given you guys some hints. I've given you the bond energies. I even gave you structural diagrams, so that should be helpful for you. All right, last problem. I'm not going to give you too many hints on this one. Just realize that this equation is balanced. Some bonds need to be broken, some bonds don't. But everything on the left side of the arrow, you're going to have to break some bonds over there. Everything on the right side, you're going to have to make some new bonds. Quick little hint, this carbon-hydrogen single bond is not technically going to be made or broken. You can kind of leave that out of the equation, but you are going to break this carbon-nitrogen single bond. You are going to break 2 moles of hydrogen-hydrogen single bonds, and then you're going to make 2 moles of carbon hydrogen single bonds, and you're going to make 2 moles of nitrogen hydrogen single bonds. Guys, I hope this helps. Just realize the point value has been increased just because the problems are a little bit more complicated. Just remember, you can always send me an email or leave a public comment on the Google Classroom. But miss you guys. I love you guys.